In this short tape produced by Mesa UK Limited, you will see two different phase changes involving CO2, which are achieved by altering either the pressure or temperature of liquid CO2. This is the phase diagram for pure carbon dioxide. The word phase was defined by the American thermodynamicist J.W. Gibbs as a system which is uniform throughout, not only in chemical composition, but also in physical state. The colored areas marked solid, liquid, vapor, and supercritical define the limits of temperature and pressure under which each single phase can exist. The solid lines indicate the pressures and corresponding temperatures under which two different phases can exist in equilibrium. For example, solid and vapor, liquid and vapor, and also solid and liquid. Both phase changes will take place in an observation cell, specially designed and constructed by Mesa UK. The cell can withstand pressures of more than 1,000 pounds per square inch gauge, equivalent to 69 bar gauge. In the first sequence, the CO2 will be cooled by forced evaporation to the stage where it passes through the triple point. The cell is filled with liquid CO2 at an ambient temperature of 15 degrees centigrade when the equilibrium pressure is 49.7 bar gauge. Venting CO2 from the vapor phase above the liquid allows more liquid CO2 to decant from the supply cylinder into the cell, raising the liquid level. When the cell is sufficiently full, both valves are closed. When the cell contents have settled, the liquid and vapor are in equilibrium. This is represented by the cross on the liquid-vapor equilibrium line. The vent valve is now open to release CO2 vapor into the space above the liquid. The pressure, and therefore the temperature of the liquid CO2, falls rapidly as it boils to produce more vapor. As the pressure and temperature decrease, the conditions are represented by a different point on the liquid-vapor equilibrium line, once again indicated by a cross. The system has now moved further down the equilibrium line. Solid CO2 begins to form. A pressure of 4.2 bar gauge and a temperature of minus 56.6 degrees centigrade has been reached. This is the triple point, the only combination of pressure and temperature at which three different phases of CO2, solid, liquid, and vapor, can exist simultaneously in equilibrium. Pressure continues to fall, and below the triple point, only solid and vapor are present in the cell. Solid CO2 is commonly known as dry ice. It has a surface temperature of minus 78.5 degrees centigrade at atmospheric pressure. The pressure inside the cell is now equal to that of the surrounding atmosphere, which is approximately 0 bar gauge, equivalent to about 1 bar absolute. The vent valve is closed. The entire cell is now below ambient temperature and will absorb heat from its surroundings. Triple point conditions are re-established as the solid CO2 melts. Now, pressure and temperature have risen, and the cell contains liquid CO2 and CO2 vapor in equilibrium. In this next sequence, the CO2 will be heated to increase its temperature and pressure to the stage where it passes through the critical point into the supercritical phase. The cell is again filled with liquid CO2 under the same conditions as before. Now hot water is allowed to flow through the heating pipes installed around the exterior of the cell. The temperature of the liquid CO2 increases, with a consequent increase in the pressure as the liquid boils. The present conditions are represented by a point slightly higher up the equilibrium line. A well-defined meniscus is still visible. The CO2 vapor above the liquid becomes more dense as the temperature and pressure increase. Critical point. The meniscus disappears and the CO2 is now existing at a pressure of 72.8 bar gauge and a temperature of 31 degrees centigrade. The critical point is the combination of pressure and temperature at which the densities of liquid and vapor are equal. Consequently, the distinction between these phases disappears, and only one phase, the supercritical, exists. The critical density of CO2 is 468 kilograms per cubic meter, which is of the same order as many liquid substances. This is nearly 3 times the density of the CO2 vapor at our starting point, which was 161 kilograms per cubic meter at 15 degrees centigrade and 49.7 bar gauge. After a small further increase in temperature, all the CO2 present in the cell is now in the supercritical phase. This supercritical CO2 has some interesting and useful properties. Its high density gives it some of the properties of a liquid. So, for example, it can act as a solvent for extracting various materials. However, its viscosity is much lower than that of most liquids, and its diffusivity is correspondingly higher. These properties have led to a great deal of interest in the use of supercritical CO2 as a safe, effective solvent, particularly for food products. Cell heating is shut off. The supercritical CO2 pressure is reduced by opening the vent valve, and the CO2 temperature decreases simultaneously. When the critical point is reached, the liquid vapor meniscus reappears. Pressure above the liquid CO2 is further reduced in stages by venting more vapor from the cell. And once again, the cell contains liquid and vapor in equilibrium.